Hi everyone, it's Mr. Glover here. Just about to get started on our next video. So the topic today is going to be solving exponential equations. Up until this point, we've focused on graphing exponential functions. So if you remember the last day's notes, we graphed functions from their equations. We went from the graphs back to the equations of the functions, and then we did a little bit with using exponentials to model problems. So today we're going to keep that theme alive with modeling using exponentials, but we're going to go through some strategies to solve it by hand rather than using graphing technology to solve all of our questions for us. So we'll start by defining an exponential equation. It's an equation that has variables as exponents and constants as bases. We can solve simple ones by equating the bases and therefore also equating the exponents. So basically, when we have a situation like we see below, we've got one base that's 4 and one base that's 8. If we can make the bases the same, so in other words, write 4 as a power of something else and 8 as a power of something else, then we can just take the exponents and we can work with them. So what I'm going to do is I'm going to replace 4 with 2 to the power 2. So 4 to the 2x becomes 2 to the 2 to the 2x. And then 8 is going to be 2 to the 3. And that's to the x plus 1. So using our exponent laws, we can simplify this expression. Multiply the 2 and the 2, so this becomes 2 to the power 4x equals 2 to the power 3x plus 3. And now at this point, base of 2 and base of 2 tells me that whatever the power is on the left has to equal the power on the right, or else these powers of 2 won't be the same. Essentially what that means is we can just disregard our base and we can go straight into our exponent. 4x equals 3x plus 3. We can then do a little bit of rearranging, subtract 3x, and we get x equals 3. When would the exponents not have to be equal? There's a few cases where you can't use this trick. For example, 1 to the power 5 equals 1 to the power 2, which is just 1. So we can't really do this with 1. We also can't do this with 0. 0 to the power 1 equals 0 to the power 15. So we can't do that. Same with negative 1. Negative 1 is going to bounce back and forth between positives and negatives. So like negative 1 to the 2 is the same as negative 1 to the 6. So because of this, we're going to put some restrictions in our equations. We won't have bases that are 0. There will be no bases that are 1. And there will be no bases that are negative. But now we've got this tool in our toolkit. We can go ahead and we can solve or rewrite some expressions using this idea of changing the base. So 27, that's 3 to the power 3. So we can use this idea that 27 is 3 cubed and 81 is 3 to the 4th. And we can rewrite this expression as 3 cubed to the power 1/3 times the cubic root of 81, which is 3 to the 4 to the power 3 over 2, or sorry, 2 over 3. The 2 over 3 comes from the cubic root. The cubic root of anything is just that number to the power 1/3. So the cubic root of 81 to the power 2 is 2/3, or 3 to the power 4 to the 2/3. It's just an application of exponent laws. So now that we've got it written like this, we can do some more simplifying. 3 to the 3 times 1/3 is 3 to the 1. And 3 to the 4 to the 2/3 is 3 to the 8/3. So now when we multiply our bases, this is going to become 3 to the 1 plus 8 over 3. which is 3 to the 11 thirds. So this is an application of the first couple chapters of Pre-Cal 11 when we spent time focusing on exponent rules and radicals. This is why you did that. Now we've got the ability to use those to rewrite expressions. A couple more of them. 9 squared could be written as 3 squared squared, which is like 3 to the power 4. 27, remember, is 3 cubed, so we could write this as 3 cubed times 3 squared. This will turn into 3 to the power 9 times 3 squared, which is 3 to the 9 plus 2, or 3 to the 11. So when we're solving equations with different bases, we need to try and rewrite them. So rewrite them so that both bases are the same. So we're taking this idea and we're using it to solve equations that otherwise we don't really have a convenient way to solve. We'll learn a new strategy for this called the logarithm, but for now, this is probably the easier way to do it. And even with logarithms, sometimes this is faster. So 4 can be written as 2 squared. So this equation could be written as 2 squared to the x plus 2 equals 64, which is actually 2 to the power 6 to the x. So doing some simplifying, the left-hand side becomes 2 to the 2x plus 4, and the right-hand side becomes 2 to the 6x. Now that we've got bases equal bases on either side, and there's no other terms, we can disregard our base, and we can just move into the exponent. 2x plus 4 must equal 6x for this to be true. And by the way, you can only do this if you've got one base on the left and one base on the right. If there's another term here, you can't just scrap the bases. Do a little bit of rearranging. So we're going to subtract 2x. 4 equals 4x. And we're left with 1 equals x. That's our answer. On the other side here, we can write 4 as 2 squared to the power 2x. And we can write 8 as 2 cubed to the power 2x minus 3. The left-hand side will become 2 to the power 4x, and the right-hand side will become 2 to the power 6x minus 9, and that's just 3 times 2x minus 3. We can scrap our bases now. We can go straight into the exponents. 4x must equal 6x minus 9. We can do a bit of rearranging here. I'm going to subtract 6x from both sides. So negative 2x equals negative 9. And if we divide by minus 2, x equals 9 over 2. Technically minus 9 over minus 2, but the negative signs cancel. So because of this, it's going to be important, or it'll be easy for you if you can remember different powers of some small bases. So we'll go through them. We've got 2 to the 1, which is 2. We've got 2 squared, which is 4. 2 cubed, which is 8. 2 to the 4, which is 16. 2 to the 5, which is 32. And I guess we could go 2 to the 6. Oops, 2 to the power 6, which is 64. And you can keep going. 3 to the 1 is going to be 3. 3 squared is going to be 9. 3 cubed will be 27. 3 to the 4 is 81. And 3 to the 5 is 243. And powers of 5, I'm not going to go as high up with the bigger numbers. 5 to the 1 is 5. 5 squared is 25. 5 cubed is 125. And 5 to the 4 is 625. For 6's, you only need to know a couple of them. 6 to the 1 is 6, of course. 6 squared is 36, and 6 cubed is 216. And if you're ever unsure, like let's say that you saw 216 and you thought to yourself, that's probably a power of a smaller number, just test some smaller numbers up. You'll quickly find not a power 2, not a power 3, not a power 5, but it is 6. And once you recognize some of these, you won't have to actually go back and check to figure out which powers they are. So alternative, we could solve exponentials on our graphing calculators. So if we're going to do this, there's a couple of ways we could do this. We could simply plot one function as y1, plot the other function as y2, and find the intersect. So step 1 would be to plot the left-hand side as y1 and the right-hand side as y2. Step 2 would be to find the intersection point. And then step 3, I guess, is going to be answering the question. The x value at the intersection point is the answer. So we can do this one on Desmos. So I'll switch my screen over to Desmos here in just a second. So 15 is one function and 3 to the x is the other. So I can plot y equals 3 to the power x as my one function. I can plot 15 as my other, whoops, I just got to define it as y equals 15 as my other function. I can't see it right now, but if I zoom out, there it is. My intersection point is right here. The answer is 2.47, 2.465 if you want. So x equals 2.47. So now, remember a couple chapters ago, we went through another technique for doing this. So if you don't want to graph two functions, your other options, well, you can do it by hand, but your other option is to move everything to one side of your equation, graph that as your function, and then find the zero. Basically, instead of y2 equal, or y1 equal 15, y1 0, and 3x minus 15 is y2. So you've got options how you want to go about solving it. It's up to you what method you want. But I find the two function method is the simplest. It requires the least amount of work, and it's usually fairly easy to do. So yesterday we worked with problems involving exponential growth or decay. These problems may be modeled by using an exponential equation of the form a equals a naught times 1 plus r to the power t. And now this is going to be the general equation for any exponential growth or decay problem. We're going to base it off of this equation, okay? We're going to have to define some parts of the equation. A is going to be the final amount. That could be final amount of dollars, final amount of people. It could be the number of grams of something. That's just how much you have at the end. R is going to be the percent change. So I'll call R the percent increasing or decreasing. Obviously, if you have an increasing function, if it's an exponential growth, it's going to be like 1 plus 0.5 or 1 plus 1. If you're decreasing, this bracket needs to be less than 1. So it'd be like 1 minus 0.5 or 1 minus 0.2. A naught is your initial amount. And T is time. Okay, so to give you an example, I'll give you an example of the half-life equation we talked about yesterday. We're going to use m instead of a. It's just because we're talking about mass here. M equals m naught times 1 minus 0.5 to the power t. And the equation turns into m equals m naught times 0.5 to the t. So essentially, every half-life we lose 50%. That's our percent change, is 0.5. We subtracted it from 1, and now we've got this equation, m naught times 0.5 to the power t. Which leads us into the next topic, compound interest. And so we're going to spend a bit of time on this. This is actually some of the more real-world application type stuff that you're going to be doing in this course, and it's actually very useful information to have. So we're going to start by defining compound interest. We'll talk about what it is, and then we're going to use exponential functions to model compound interest problems. So with compound interest, so compound interest, the principal A naught dollars is invested at an annual interest rate of I. This interest is then added back to your principal, which is known as compounding. After a given amount of time, which is called the compounding period, we can create an exponential equation to solve for the amount of money available in t years. The equation, with a principal of A naught dollars invested at an annual interest rate of I should probably put that lowercase I, with n compounding periods per year, the amount A dollars will be available after t years. So we can write it off to the side. In this equation, I equals interest rate. N is the compounding periods per year. And T is the number of years. And technically, A naught is your starting amount. A naught is the starting amount, or the amount invested. So basically, to explain the idea of compound interest, there's the concept of interest is that interest is basically, it's an incentive for somebody to loan money to someone else. So like if you wanted to borrow money from me, let's say you wanted $1,000, I probably wouldn't just hand you $1,000 without some kind of incentive for me to do that. I might say, well, if I give you $1,000, I expect to get $1,100 back from you. That's the concept of interest. But usually interest is a percentage of the amount owed, and it is calculated based on how much money you borrowed. So I would say I want 2% back, or I want 3% back, okay? Now, there's a couple different types of interest. There's simple interest and compound interest. Simple interest just means that every year you get the same amount of money back. So I'm gonna, maybe I'll switch the screen here. Say we're doing simple interest. Okay, let's say you borrowed $1,000 and you're charged, I don't know, 2% interest annually. Okay, so if we were doing simple interest, and let's just say year 1, 2, 3, and interest earned, every year you're getting the same amount of money. Every year you're just getting 2% of that $1,000 that you borrowed. So year 1, you're getting 20 bucks. Year 2, still getting 20 bucks. Year 3, still getting 20 bucks. So it's based off of the amount earned, okay? Compound interest, on the other hand, compound interest is based on the amount present in the account at any given time, okay? So let's take a similar scenario with compound interest. Let's say you invest $1,000, compounding at 2% annually. So exactly the same numbers. All right, we'll go year and interest, or maybe I'll have a second column now for the balance and interest earned. Okay, so in this scenario, in year 1, you have a balance of $1,000. That's how much you put in. So the interest earned is going to be 2% of that. It's going to be $20. All right. Now, in year 2, your balance is up to $1,020. It's a little bit more. So when you go to calculate 2% of that, it's going to be slightly more than 20 bucks. It's going to be $20.40. So then the following year, you're now up to $1,040.40. So the interest earned is going to be 2% of that, which is $20.81. So as you can see, with compound interest, because you're basing the interest earned on the balance of the loan or the balance of the investment, you're going to slowly see the interest earned increase because you're earning interest on interest that you've made previously. It doesn't seem like a lot, 40 cents, 80 cents, but if I move these digits over, if instead of $1,000, we're talking like $10,000 or $1 million, this goes from 20 to 200 to 2,000. Then instead of 2040, we're making 2,040. Things start to become important here. And compound interest is actually one of the more important things to know about because it allows you to grow money very, very easily if you invest it wisely. It also allows you to shoot yourself in the foot if you take on a loan with a really high interest rate. And we'll explore that in the coming days. So anyways, back to our notes. We've kind of talked about what compound interest is. Now let's model it using these exponential equations. So last summer, Tim got a job in the oil patch, managed to save $10,000. He decided to invest it in a college fund for the next 10 years while he goes and travels, so he can go get a math degree after. Find out how much he will have if it grows at 6% annually. Okay, so we're going to start by writing our base equation. A equals A naught times 1 plus I over n to the power nt. We're going to list out our variables. Tim had an initial investment A naught of $10,000. He is earning an interest rate of 6%. So we've got to be really careful. 6%, if you divide by 100, is 0.06. You've got to use this number, not this number. Number of compounding periods per year and annually, so n is just going to be 1 compounding period per year. And he's investing it for 10 years. So we can plug our numbers in now. And this formula will turn into 10,000 times 1 plus 0.06 over 1 to the power 1 times 10. This simplifies to 10,000 times 1.06 to the power 10. And at the end of the day, 10 years later, Tim has turned $10,000 into $17,908. So interest is a very important thing. In the matter of 10 years, Tim's almost doubled his money. He's gone from 10,000 to almost 18,000. So this is a really important thing to know about because this is something that goes on all around you all the time. And if you want to grow your money, you need to understand how compound interest works. We're going to change this to monthly now. So all the numbers are the same except n. Okay. So A naught is still 10,000. I is still 0.06. T is still 10 years, but now we have 12 compounding periods in a year instead of 1. So going back to our formula, A equals A naught times 1 plus I over n to the nt. We can plug in our numbers, 10,000 times 1 plus 0.06 over 12 to the 12 times 10. This simplifies into 10,000 times 1.005 to the power 120. If he compounds his money monthly, which what that actually means is that once a month, the interest is calculated based on your interest. Instead of 17,908, Tim will have $18,908 900 or 194. So he will have slightly more money if it compounds monthly, and that's because the more frequent your compounding periods are, the more often you're gaining interest on your interest, which means you will make slightly more money because more interest is included in your balance. If you only compound once a year, you're only getting interest on interest once a year. If you compound it daily, then your balance is slowly growing every day, and you'll notice it with slightly higher numbers. It's the same reason why when you're seeking out a loan or you're seeking out a investment, you want to go for the one that has the lower or the more frequent compounding periods, assuming everything else is the same. Number one is interest. You want the interest rate to be low when you're borrowing and high when you're investing. But if everything else is identical, pick the situation where you've got more frequent compounding periods. All right, so we've got a couple more problems and then we'll be done for today. Dakota plays in a punk rock group called the Denominators. When their band grows, he will need to get a new guitar and amp, so he decides to put his earnings from his last gig into a savings account in hopes that it will grow. Dakota has $1,000 to deposit and needs to decide between two bank accounts. Account A has an interest rate of 7% annually, compounds annually. How much money will he have with account A after 20 years? Account B is 6% annually, but it compounds monthly. How much money will he have with account B in 20 years? Before we do the math on this, I want you to think about if you were to walk into a bank with $1,000 and you had to choose between these accounts, which one do you think you would pick? If you're following my advice, you'd probably go for 7%, but this one is just slightly lower and it compounds more frequently. So this one might be tempting to you, okay? Think about the numbers and we'll go through the math on it and you'll see why it's a big deal to go with the right account, okay? In this scenario, A naught is 1,000. That's how much money he's investing. The interest rate I is 7%, which is 0.07. It compounds annually, so N is one compounding period per year, and T is going to be 20 years. All right. In the other scenario, A naught is still 1,000. The interest rate I is still it's 0.06, not 0.07. N is different though. It's compounding monthly, so N is 12, but the term T is still 20 years. All right. So using our formula, A equals A naught times 1 plus I over N to the NT. A naught is 1,000 times 1 plus 0.07 over 1 to the power 1 times 20. If he goes with account A, he will have $3,870 in 20 years' time. Which is, I mean, it's good and bad. He only had $1,000 to invest, so that's what you got to keep in the back of your mind. He has almost quadrupled that. He's also waited 20 years. So inflation will catch up to him, and inflation is going to make his $4,000 not worth as much as it would have been 20 years prior. But that's a topic for another day. In this scenario, using A equals A naught times 1 plus I over N to the NT, we can plug our numbers in. $1,000 times 1 plus 0.06 divided by 12, the power 12 times 20. He will only have $2,712 if he was to choose this account. So when you sign up for the account, it doesn't seem like much is different. 6% versus 7%. This one's annually, this one's monthly. It looks like it'll all come out in the wash, but this one, he's barely tripled his money. This one, he's barely quadrupled his, well, this one, he almost triples. This one, he almost quadruples. So it does make a big difference. If he invested $100,000, I would rather have almost $400,000 than almost $300,000. So which account should Dakota put his money into? I would go with bank account A. So there's some problems for you to try here. It looks like a lot of questions, and it is actually quite a few questions, but keep in mind that the starting questions, you're only doing 1 or 2 of them out of each question, like 3 through 6, you're only doing A and C. And a lot of the early questions are simply rearrange this equation or rewrite this number. It's only when you get up to the end that you're actually solving these more complicated problems that take more time. So I think I'm going to end the notes here today. I hope everybody has a great rest of the day, and I will see you all in the chat tomorrow. And give these questions a shot so that when you come to the Zoom meeting, you've got some questions to ask about your assignment if you have them. Anyways, bye for now. Everybody have a great rest of the day.